So we know we have these functions. Now we want to assign variables to these functions. So I can assign just variable 1, 2, 3, 4, 5, 6, 7, 8, and I can have all 1,000 data points, but I can change the mean. And so these have 10, but then their standard deviations are different. So maybe they're using different engineering tools. You know, some of the tools have a bigger standard deviation, they were cheap. Some of the tools have a smaller standard deviation, they were more expensive. We could also change the mean. Maybe on average, there is a different initial temperature or final temperature for this metal. And so we would shift it, the mean over. And then maybe they were all using the same tool, the same temperature tool, and it all had the same standard deviation. So there are lots of different ways that you can generate this set of random data. Now, again, just to show you how quick it is to get a big data set, here is a graphing example where we just installed Tidyverse, and specifically the library that comes with Tidyverse. And you may have used this particular library in your biostatistics. Many times in biostatistics, you do this vehicle analysis and do statistics on US vehicles or international vehicles. So we download this library with 2 lines. It's just 2 lines. It installs it very quickly and easily. Well, I said quickly and easily. Yep, there we go. And then we can actually say, hey, grab this MPG information from here. So it graphs it. I mean, it plots the table of what is located in MPG. So I only had 1 line of code, and then I got this whole data output, which is the vehicles, engine displacement, type of vehicle sold, the year it was sold, the engine size, something about the transmission, and the fuel economy for city driving and for highway driving. Okay, and then you do 2 more lines now, and now you can graph it. You can graph the engine size and the highway fuel economy. So the larger the engine, the lower the fuel economy. Well, the larger the engine, the more power you have. If you have more power, your fuel economy is going to be less, because fuel economy is related to the efficiency of the vehicle. So within 5 lines of code, 1, 2, 3, 4, 5 lines of code, I'm able to get all of this data here and plotted. So that's pretty easy, much, much easier than if people were to give you a Google spreadsheet of all the vehicle data and then have you actually create a graph in there from that. It's not totally convincing that this is much easier. So we'll do a little bit extra to show how much easier it is. So we'll look at some of this random data that we created. So we created a set of random data here. And let's just look to see if that random data that we created was in fact a Gaussian distribution, because we claimed it was a Gaussian distribution. And I'll have one person share theirs. Nicole, could you share, after graphing simulated data, what yours looked like?
Yes. Do I just run it really fast and then that'll show like the new one?
Mm-hmm.
Okay.
We're not going to be able to see it unless you hit clear, share screen though.
Oh yeah, sorry. I don't know what's going on with I updated my computer and it's saying I need to figure out how to share the permissions with Zoom.
Oh, okay. Hold on. Let me see, make sure that you should be able to share, or maybe you're having trouble.
Oh yeah.
Can you do it? If not, we can switch to someone else. It's okay.
Okay, sorry. It might take me a second.
No, it's fine. It's fine. Catherine, what about you? Were you able to do it?
Yes, I was able to do it. Would you like me to share my screen?
Ava, try it again. Click run all and see if it'll do it.
Okay, can you see my?
Yeah. So do you see that yours is at 10? So your mean is at 10, which is what we set it to be.
Yes.
Now, if you were, I can actually look at yours and look at mine. You can only see yours right now. But as I look at yours, your value for your mean, there's about what, 100 and maybe 80 or 90 incidences where they're around 10. And to the left of yours, it's actually bigger. There's more incidences slightly to the left at 9. And it's at 11, you're a bit lower. And mine is equal at 9, and my 8 is actually much lower. So let me share everyone my screen. So can people see my screen now?
Yes, ma'am.
Okay. So in this one now, you'll see mine are actually equal and this one's lower, not higher. So your Gaussian distribution will in fact have a mean of 10 and have a standard deviation of 2, but everyone's data will be slightly different because we used a random number generator. So just to be aware that you shouldn't expect exactly what I have on my screen because you have your own random data. Does that make sense? Everyone? Yes, no? Yes.
Yes.
Okay. So now if we go to, okay, so where in the world are you going with this? This is not physics right now. Well, now we're going to make it physics. Okay. So let's say we have a bunch of simulated data, but that simulated data is supposed to be masses. And then we take the masses and we're going to multiply the masses times 9.81 meters per second squared to get the weight. And we're going to just call the masses x-axis and the weights y-axis. So we can actually plot this now. And when we go to plot it, the very first one is the simple plot. And you'll notice that one has no title and it just writes down on the axis whatever you put inside here. So the second one is actually much better of a plot because now we can change the name of the axes and the title. And later on, we'll have some features to be able to actually easily add error bars and minimum and maximum. So we just push that button and it immediately generates. We don't have to click through all the Excel options. We don't have to like highlight columns and like, oops, I accidentally hit 2 columns and now it's doing a series instead of just the data that I want. There's no fighting about it. You don't have to futz with it. You just push this little button here and it generates a graph for you. So this is going to be a set of data. And then this is what we're going to calculate. Now let's see, we can use not only a linear function, let's say we want a sinusoidal function. So we can actually use the sine function. R will have all of your normal mathematical functions, tangent, cosine, exponential, logs. And there's a cheat sheet for all of that. You can just do R language cheat sheet and you can see what all of the coding is for that. So now we have data. And remember our data was Gaussian. It was, you know, the mass was 10 and it was plus or minus 1 standard deviation was 8 to 12. But every now and then we might have measured it to this particular data to be a little bit more or less. We might see some others. So when we put it into the sine function, it makes sense that it's not evenly distributed in this sense. If we had done a string of values for X where they were equally distributed like we did for the variable B, then you would have equal data throughout. But in this case, we don't.